Does this belong to you, any of you? If this belongs to you, please come and see me after the lecture. If you don't, I will give you 0 mark. I will give this 0 mark because it has no name and it has no ID. Okay? All right. Last Thursday we talked about the binomial distribution. So I just want to review. What we did last Thursday. So this is the PMF of the binomial. This is the CDF of the binomial. All right. These are the ARC commands. These are the ARC commands for computing the PMF and the CDF of the binomial distribution. Right. And these are 2 basic properties of the binomial. I'm sure all of you know this already. And this is estimation, right? If you have a random sample from, thank you, ma'am. If you have a random sample from a binomial distribution, so this random sample could represent, for example, like the number of times you get a head. You should toss a coin 10 times. So each of these numbers could be anything between 0 and 10, representing the number of heads you get. You should toss a coin 10 times and repeat that n times, right? And an estimate for p is given by this formula here. So 1 divided by m times n multiplied by sum of xi. Then I did 3 examples. This is the first example, which is trivial, right? This is the second example, which is not really difficult. Okay, and this is the third example. The third example, I couldn't do it because you get to a formula like this, right? And you can't compute this formula even with the computer, because the numbers are so large, right? And this is where the central limit theorem comes in, right? So I introduced the central limit theorem, which is this one here. It says that this guy here approaches the standard normal as n is the sample size goes to infinity, right? But the sample sizes can never be infinity, because in practice nothing is infinite. Okay, so you can only approximate this guy here by a standard normal for if given that n is large enough, right? So from this statement, you can derive this statement, which implies this, which implies this, and finally, after some calculations, you get to this, right? You get to the statement that the probability that the sum of xi is less than or equal to z is approximately equal to this. Now, I'm going to show you how to use this to solve example 3. So, all right. Okay, suppose x1 to xn are in IID means independent and identically distributed Bernoulli random variables. I'm sure you did this before. Don't tell me that you don't know this, right? Then this implies that the sum from what you did in probability 1, right, would you know what distribution will this have? If you have IID Bernoulli, then the sum of them has what distribution? Come on, guys, talk to me. Okay, some of them, do you know this result or no? You don't know? Yes? If you don't know, just, I mean, it's in this handout I gave you at the beginning of the class, of the course, right? So this implies, now going back to this statement here, which I proved last Thursday, right? This implies that the probability that okay, so the probability or the CDF of a binomial random variable can be approximated by this if n is large, for n large. Okay, so going back to example 3, let me go back to example 3 now. Example 3, which we did last Thursday, was to find the probability that x lies between 100 and 100, right? Okay, so so the probability that x here is 1,000 with parameters 1,000 and 0.2. We want to find the probability that we want to find this probability, guys, all right, that a binomial variable with these parameters is between 100 and 200. Now this you can write as follows. Right? Okay, this statement is the same as this statement here. Okay? Now, let me put this back here. Now I'm gonna okay, let me call this star. Okay? I'm going to use star to approximate these probabilities. So this will be an approximation, not exact, right? So using star, we will have the following. We will have phi, n is 1,000. Sigma, I will come to what sigma in a minute, okay? That is right? Okay, guys, are you with me or not? Do you see how I got from this line to this line using star? Now, this is where you need to determine what your mu and sigma is. Remember, mu is the mean of x1 to xn, And sigma is the standard deviation, or the square root of the variance of x1 to xn. So this is where I need to figure out, let me draw a box here. I will draw a lot of boxes here, but mu is the mean of the xi. Now we are assuming each xi is a Bernoulli variable. So what's the mean of that? You should know this from probability 1, guys. What's the mean of a Bernoulli random variable? It's p, right? I mean, look at this, guys. You should look at this handout, which you should have, right? It will tell you what the mean is. And the sigma squared is the variance of xi, which is again Bernoulli, is p times 1 minus p. So sigma is simply the square root of p times 1 minus p. Now in this question we are assuming that p is 0.2. So mu is 0.2 and sigma is the square root of 0.2 multiplied by 0.8. You follow how I got it? Yeah? Just using the fact p is 0.2. Okay? So going back to this line, this becomes phi divided by sigma, which is 0.2 minus 0.2, which is 0, right? Minus phi divided by 0.2 times 0.8. 99 divided by 1000 is 0.099 and 0.2. All right? And this you can calculate using tables. Okay, I'm not going to do that because it will take me time. We are running out of time. Okay, is that okay? Is that clear, guys? Now, how I use the central limit theorem to compute this probability here, that the probability that a binomial with such large numbers, which you can't compute using a computer, right? So you have to use the central limit theorem in this case, right? And so the approximation I have made is using star, right? Star says that for n large, you can approximate this by this. And that's what exactly I have done here. From this step to this step, that's what I did. And then I worked out the mu and the sigma. Mu and the sigma are simply the mean and the variance standard deviation of the x1 to xn, which we are assuming to be Bernoulli, right? So mu is 0.2, sigma is the square root of this. And you sub them here, you get this. And you can work this out using the tables. Any questions, guys? Are you guys okay? All right, so we need to move on quickly to the next topic. So we are done with binomial. The next topic is the following. The next topic is sampling distributions. right? Sampling distributions are distributions of functions of data, right? And in this course, I will talk about two sampling distributions. One is known as the chi-squared, and is denoted by this Greek letter. This is the Greek letter. And the other one is known as student's T. It's denoted by T, basically. And there's also a third one, which I will not talk about. It's known as the F distribution, right? Okay. Right, so I will only talk about the first two, the chi-square distribution and the student's T distribution. Right? These will be useful later when we talk about confidence intervals later in the course. Okay, so let me start with the chi-square distribution, right? I don't know whether you covered this in probability 1 or not. Did you do this in probability 1, guys, or no? Okay. Oh, come on, guys. All right, chi-square distribution in one of the sample. I will explain in a minute why it is a sampling distribution, but before that, let me introduce some terminology, right? So you say a random variable x has the chi-square distribution and it's denoted by, this is the notation, and a is a parameter, which I will introduce in a minute. If x is defined on the positive real line, and a is also a positive parameter. So a is the only parameter and is positive, and a is referred to as the A is referred to as the degree of freedom parameter, okay? Okay, guys? And you should draw a picture of this. I'm not good in drawing, but as you will see how bad I am in drawing in a minute. Typically, the shape of a it looks something like this. This is the PDF x, fx of x, PDF of, right? So the PDF of a chi-square density or chi-square distribution it's kind of skewed. It's not like normal distribution, which is symmetric. This is skewed, right? Now R commands I know R is really, I mean, this week, by the way, we have no lab sessions, but instead we have tutorials. Please do come to the tutorials. I will be taking attendance, okay? The R commands are as follows. So hello guys, you okay? So this command here, D DCHISQ in brackets x comma df equal to 2. Df stands for degree of freedom equal. So in this case, a, the parameter a takes the value 2. So this command will compute the PDF of chi-squared, which is this one, at the values given by x, right? And this command here is the same, except it starts with P. PCHISQ in brackets this. Right? It computes the values of the CDF of this variable, right, at a equal to 2 and at the values given by x, right? All right. Next thing, next thing is percentiles. I mean, I don't know whether you know what percentiles is. Let me explain what it is. Basically, so this guy here, this notation, chi-squared alpha is a subscript at a, is the value for which the probability that a chi-squared variable is less than or equal to this value is alpha. Now there are tables for reading this guy here. But once again, you should go back to the thing I gave you at the beginning of this course. There's a, or I will show you the table. This is the table I'm referring, which is known as the chi-square table. Can you read this, guys? Maybe better now. All right. This is known as the chi-square table. So if you want to read, right, suppose you want to read chi-squared 0.9 at a equal to 2, right? It's simple. So all you have to do is you look for 0.9 along the first row, which is over here, right? This is, oh, there's no 0.9 here. Let's change it to 0.95, sorry guys. Okay, so you look for 0.95 along the first row and 2 along the first column. So you get the value this. So this will be 5.991. So what it says is that, what this implies is the probability that a chi-squared variable with 2 degrees of freedom is less than or equal to 5.991 is equal to 0.95. That's what this means. All right? So let's look at another example. Say chi-squared, say 0.01 at, say 15, right? So to read this, all you have to do is look for 0.01 along the first row, which you are here over here, and then you look for 15 along the first column, right? So you get this guy here. Can you see it? You get 5.991. 5.229, right? 5.22. So this will be 5.229. So what this implies is that the probability that a chi-squared variable with 15 degree of freedom is less than or equal to 5.229 is 0.01. All right? So this table will be useful not at this stage of the course, but when we come to talking about confidence intervals and tests of hypothesis, we will use this table a lot. Okay? But at this stage, I just want you to know how to read the chi-square table, right? All right, guys? Okay. So these are, oh man, these are percentiles, okay? Right, next thing is some properties. I'm going to write some properties of the chi-square distribution. And once again, properties. Once again, I don't expect you to know the proofs. I mean, but if you can prove them, that's fine. Okay? So properties of a chi-squared variable x that follows the chi-square distribution with parameter a. Okay? Number one, the mean or the expectation of a chi-squared variable is equal to a. Number two, the variance of a chi-squared variable is equal to 2 times a, right? Number three is that if IID, remember IID means independent and identically distributed normal variables, then right, this is a very important property. Listen, guys, which says that if you have a random sample or IID variables from a normal distribution with parameters 0 and sigma squared, then this guy here has a chi-square distribution. And what you see on the left-hand side, the LHS right? You see, the left-hand side, if you look at the left-hand side of this, what you see is a function of the data only, right? Nothing else involves apart from the data, right? And the RHS involves the distribution. And this is exactly why right? This is remember at the beginning, a few minutes ago, I said to you guys that a sampling distribution is a distribution that's a function of the data only, right? And what you see here is on the left-hand side, you have you have a function of the data only, and that follows the chi-square distribution. And that's exactly why chi-square distribution is a sampling distribution. Because any distribution that arises as a function of the data only is a sampling distribution. And this is the reason, this here is the reason why chi-squared is a sampling distribution. Okay? All right, that's number 3. Let's go back here, let's go here. Number 4, property number 4 is the following. Right? If you have 2 independent variables, x and y, x has the chi-square distribution with parameter a, y has a chi-square distribution with parameter b, then x plus y will also follow a chi-square distribution with parameter a plus b. Right? And this property is known as the closure property. Closure, if you want to know the name, this property is known as the closed under sum, meaning that if you take a sum of independent chi-squared, then it's also chi-squared. All right, so that's why it's closed under sum. All right. Number 5, if x is a standard normal variable, right, then the x squared is a chi-squared variable with 1 degree of freedom, right? Okay, that's number 5. And number 6, this is the last one. I don't mean to bore you. If right, if you have xi, sorry, I should say I from 1 to n, okay, I from 1 to n, right? Okay, then the following is true, okay? Right? By the way, the tilde, this notation here, which is known as a tilde, it means distributed as, okay? I hope you know, I mean from probability 1. Whenever I use the notation tilde, it means distributed as, right? Okay? Okay guys, so these are the 6 properties, and once again, I don't expect you to know any of the proofs. And if you want to know the proofs, you can contact me or whenever. Okay, so let me do an example. suppose you have n random variables from a normal distribution with parameter 1 and 1, right? Shh. Listen, guys, please. Calculate the following probability that this guy here is greater than 3. Now, how would you do this, guys? Now, you need to use, remember, one of the properties I talked about is this one here, which says that this guy here has this distribution. So we can write this as the probability that okay? Are you with me? Okay. Now, because of this property, guys, we know that this guy should have this distribution. So by property 3, right? Sigma squared is what here? Sigma squared is 1, right? Because we are assuming mu is 1, sigma is 1. So sigma squared is 1. So this is chi-squared n minus 1 greater than 3 times n minus 1. You follow me? Yeah? Okay. Now this you can write as 1 minus the probability and of course, you know the value for n. So for example, if n is 10, you will be able to read this from the table I gave you, right? This table here. So without an n, you need to leave it like this because you can't compute this, right? But if you know n, say for example, n is 5, you can read this probability of this table, okay? So that's the example, okay? So it's not a difficult example, is it? Yeah. Right. The next, okay, that's the chi-square distribution. The next distribution, I said they're going to talk about 2 sampling distributions, right? One is chi-squared, the other one is t. It's also known as student's t. So the next one, all right, I'll just introduce it because I don't think I will have time to talk about it a lot. So the next sampling distribution is known as the student's t distribution. This is due to this distribution is due to William Gossett. Is he worked for the Irish company, the beer company. He worked for Guinness, the famous beer, Irish beer, and because one of the policies of the company was that you're not allowed to put your research in the public domain. In other words, he cannot publish he was not able to publish his findings, right, outside of the company, right? So he published his findings under a pseudonym, which he called Student. So that's why it became known as Student T-Distribution, right? Because just not to reveal his identity, right? Okay? Okay, so maybe you know the story already. I don't know. So the sorry, my spelling is wrong. It's Guinness. They should be double N. All right, Guinness. This is the notation I will use. A little t with parameter a. If his PDF is the following. Right, this is the formula for the PDF, or the density function of a t variable, or student's t variable, right? And once again, there is only one parameter a, but this time x is defined over the entire real line, okay? And a is, as before, is a positive parameter, and once again, a is referred to as the degree A is referred to as the degree of freedom parameter. Okay? And you should try to plot the density of the t distribution on a paper. It will look something like this. Once again, apologies for my drawing abilities. I wish you should. Let me try to look. This is F. Now, what does this remind you of, guys? I mean, if it looks something like, what does it look like? Huh? Come on, guys, talk to me. Why are you afraid of me? I'm being nice to you guys. This looks like what? The normal distribution, right? Yeah, okay. So the only difference is the following. Now, all right. This is the PDF of a t distribution, right? Now, on top of this, if you plot the PDF of a normal, it will look something like this. Sorry. Hopefully I'm not going to make a mess. So what I'm trying to do here, guys, is I'm plotting on top of okay. So what I have, this guy here is the You see the difference between the two. They are both symmetric around 0, right? They both look like a bell shape, but there's a key difference between the two. The key difference is that the PDF of the normal distribution, it decays to 0. It decays to 0 much faster. So this So the PDF of the normal distribution decays to 0 much faster than the PDF of the T distribution. That's the key difference. Apart from that, both of them look similar, right? The PDF of the T distribution decays to 0 much slower, all right? Okay, guys? So that's the key difference between the normal and the T distribution, right? All right. Next thing. The next thing is I'm going to show you the R commands, right? I will finish after this. You're tired already. The R commands as follows. So this command here, d, small d, t, in brackets, x, comma, df equal to 2, computes I should say computes PDF of. So it computes the PDF of, or the PDF of a T distribution with 2 degrees of freedom at x. And the following command, it computes the CDF of at x. All right? Okay, guys, so these are 2 commands that we will use later when we talk about confidence intervals and so on. Okay? So on Thursday, when we meet on Thursday, I will finish sampling distributions and talk about an important topic, which is estimation. Right? So I will start talking about estimation on Thursday this week. Okay, guys? Now, before you leave, I've got a quiz without a name. So if this quiz belongs to you, can you please let me know? Because this quiz has no name and no ID. So I'm going to give this quiz 0 mark because... So if this is yours, can you please come and see me now, please?
fine, thank you, sir.
Not many people come to my class.
I'm sorry?
Not many students come to my class.
Yeah, I expect the same. I expect the same. There wouldn't be many today.